So this is lecture 27, and in the last, like 27, right? So in the last class we looked at an oscillator. We are still looking at oscillators, and the thing which you were considering was a ring oscillator. So let me just give a brief recap of what we were doing. So this is an oscillator, and all these oscillator has control nodes. This is, you can call, let's say, V low, and in our cases we normally connect it to ground, and this is V high, and this we normally connect to VDD. You can say VDD or V control, whatever. Normally this we connect to VDD. So in this kind of oscillator, we see that the just remarks on this oscillator are that this is a high swing oscillator, and high swing is the output voltage. Let me call this as V out, and the other things were, so I think the last thing which we look for, how to tune the frequency of the oscillator. So tuning clock frequency, and here we looked at different ways. First one was we looked at you can change control voltage. Which was actually your V high. In this case, you keep the other node as ground. Second one was you use a current starved inverters. These are different ways in which you can control the frequency of the oscillator. Current starved inverters means, I think this we saw, that I control the current of the inverter. So this one is VBP and VBN. This I am generating for a desired current, and my ring oscillator is this. So this was the current starved inverter, and the third case was you vary the capacitive load at each node. Capacitive load for inverters. Okay. So most often, like quite often, I can say that if you want to have a wide frequency oscillator, which you want to have an oscillator range of, let's say, 2x, means you want to go from 2.5 to 5 gigahertz, and that too you want to have a process variation, PVT variations to be compensated. You use either your A and C or B and C. There's nothing. So A and C, you are directly varying the control voltage, and you can have the capacitive loading. Mostly use capacitive loading to compensate for process variation, and control voltage to vary the frequency. And B and C means this is just a different way. Either you are controlling voltage or you are controlling current in the two cases. And the third one is the capacitive loading. Okay. Anything on this? So now this oscillator has to be, so the starting for today's lecture will be that I have this ring oscillator and I want to control. So normally this is the control voltage, V control. So let me just connect everything else to ground, and this is V out, right? And the transfer function which we are looking for this VCO is that what is the frequency F out as a function of V control. This is what we want to have. And normally we define this thing as KVCO, where KVCO is in Hertz per volt in this case. Okay. So we are not looking for V control to V out transfer function here. We are looking for V control to the frequency translation. Okay. Now this, so and I think the earlier, yes, in the last class we also see how this V out you need to buffer it at the output. So that part is done, right? So now the thing is, where is this V control coming from? we know that this V control should be the output of the loop filter, because that is what we have seen in our block model, right? Block level diagram of the PLL. So the first one way is I can directly connect these two. Okay, and directly connecting these two is, if you look at a pros of this kind of connection is that as your control voltage vary, so does your supply of the ring oscillator vary, so does your power consumption in the ring oscillator will vary. So mean as your frequency, you do not have to worry about whether the power will scale or not with frequency. Here it will automatically scale with the frequency because the current is coming. So the power in this case scales with frequency. In another case also it scales with frequency, where here there is no other block in between. It directly scales with the frequency. There is no other static power consumption in this. Okay. And you need to maintain this weak control voltage above certain level such that this ring oscillator can oscillate. The transistors can trigger. Okay. And but what can be the bad part of this can be? Pardon? It loads the filter, so that's fine. It loads the loop filter. So what will happen if it loads the loop filter? Huh? Yeah, so this will actually lead to you offset. So mean you can say the charge pump seems to be always on. Means always on, or there are large offsets in the charge pump. Whatever the current has been taken from this capacitor, that has to be replenished by the charge pump every clock cycle. So charge pump operates with input offset. Okay. So, and if the charge pump operates with input offset, then you will have an added charge pump noise. You will have an added charge pump added ripple due to the charge pump current. Okay. So, what could be the easier way to do? In place of making this connection, I can. So, what I have is I have the sorry. So, I have the loop filter, and let me just mark the VCO as something as V control, and I'm just writing this as VCO, means the supply as the V control node. So what I can do is I can put a unity gain buffer. Okay, so let me just call this as V loop filter and this one as V control. Okay. In this way, no current is coming from the loop filter. All the current is coming from the op amp. Okay. So for this, no current drawn from loop filter, which will basically like remove all the charge pump problems which we had before. Okay, loop filter, but it comes with another thing. You have a current requirement on the op amp depending on the current requirement of the VCO, right? So the static current consumption in the op amp actually goes high, increases. And this is not linear increase. You want to operate this op amp as a linear block, which have ideally you want to have a V control of S by V loop filter of S equals to 1 for all the frequencies of consideration. And you know you are realizing this op amp using transistors, so you need to operate in the linear region, which means that the current consumption in the op amp should be much higher. Okay. So what is the then a more in order to relax the op-amp, what we can do is we can have an op-amp control, but a bypass transistor to the VCO. Okay, so this is V loop filter of S. This one is V control of S, and this is VDD. Okay, so now in this case, pardon? Okay, yeah, there's one inversion with the PMOS. Okay. Okay. So now you have a means you relaxed op-amp requirement. Then now the only thing is maybe for some bandwidth requirement you need relaxed op-amp static power consumption requirement zoom, and all the power is coming from the bypass transistor. Okay, so now the one other thing, in case when you're using an op-amp directly, you can say that the output swing for this, let me just make a line here. The output swing for this kind of regulated, this is called a regulation of the VCO. This kind of regulated VCO has an output swing which is limited by the op-amp swings, right? Good swing is limited by op-amp. Okay. So whereas when you are having this bypass transistor, here you can say the output swing, the upper limit of the output swing is means you can say if we operate V control voltage is less than equals to VDD minus V overdrive for the PMOS top PMOS transistor. So this is M0. Let me just call this as M0. This is the maximum you can go, and the minimum is for sure 0 in this case. Okay. So your output swing is not limited. So any drawback in this kind of VCO? In this kind of, so what we wanted to control the supply of the VCO to control the frequency. We did not want to load the loop filter. We did not want to increase the power consumption in the op-amp like 4 or 5 times because we have to operate in a linear region. So all these problems are gone and solved in this case, right? And this is quite often this is used as a regulated VCO in the designs. But what is the problem in this? Yeah, so bandwidth has to be very higher. That might be fine. So that let me just put it this way. What decides the bandwidth in this kind of regulation? You have to think about it. So depending on the current in the VCO, you will have one capacitor here, which and depending on the load on the VCO, you will have another capacitor here. So these two poles normally come as a dominant, means either of them can play as a dominant pole. Now, this is a unity gain buffer in the end. And unity gain buffer achieving a bandwidth is not that difficult, I would say. Means it's not that you can just neglect it, but you have to keep the bandwidth. In both the cases, the bandwidth of this loop, let me just say that this is regulation bandwidth and regulation bandwidth in the loop which I have marked, bandwidth for VCO, you can keep it if it is like greater than 5 times of omega PLL. It is good enough. And surely you will have a consequence on the whole bandwidth and the loop gain and all the parameters, but if you keep it this way, you will have it means it's not that difficult to maintain that. Take an example, right? You use normally a frequency of 100 megahertz as a reference. lesser than 100 megahertz. Bandwidth is FF by 10, which is 10 megahertz. I'm asking to have a 50 megahertz bandwidth in a unity gain thing, right? And again, it depends on the current consumption and what all things are there loading. One other thing, since I will go against, one other thing I can tell you here that this particular, so this VCO itself is always consuming some amount of current. This is slightly off the track, but this is important to mention here. This VCO always consumes static power current, so this VCO can be modeled as a resistor, right? This I'm modeling as, let's say, as a RVCO. And if whether there's some amount of cap is there or not there, whatever the cap appears here, right? This particular cap, so let me call this as CVCO. This whole RVCO and CVCO, this can be modeled as one other additional pole in your system, right? And you remember that we have to put the third pole. We started with 2 poles in the system at S square. We introduced 1 0, but in order to suppress the reference spur, we introduce another pole with C2, right? So either you go and put a C2 there, or you can realize this by putting a cap and put this pole at a higher frequency which you want. So you're getting my, so the thing is, because I'm putting a cap here, that's why I'm summing it. So in an actual, we started with the loop filter with a single capsule C1. We change it to RNC1. Then we put it 2 poles to suppress the reference spurs. We put this thing, right? This is what we did. What I am saying is you can still use this same thing in your PLL in place of putting a second cap, right? And you can use, you already have a R here. You can use another cap, whether it is already there, you can add to the cap to realize the second pole in the system. This you can do it easily in a ring VCO. Okay, that is slightly off the track, but in case of this regulating the oscillator bandwidth, this is most commonly used. Now the other thing is you can say that this regulation bandwidth has to be higher than the PLL bandwidth, otherwise this is going to limit the whole loop bandwidth. And the thing is, these are 2 poles, so this is omega A and this is omega out. And depending on whether the 2 poles are lying close to each other, you may have to compensate this loop. Okay, so you can use a Miller compensation or make one pole as a dominant pole. You can do that part. Okay, now the difference between the two of the designs where you are using directly as an op-amp as a unity gain buffer and op-amp with a bypass transistor mostly come in terms of power consumption is one thing. In one case, power consumption is higher. The other thing is the power supply rejection, power supply noise rejection. So in this case, where your VCO output is completely controlling, your op-amp output is completely controlling the VCO supply, the power supply rejection, supply noise rejection for this VCO is directly dependent on the power supply rejection ratio of the op-amp, right? Now, if we can realize an op-amp with a high common mode rejection ratio where the outputs do not change, or some like a very an ideal op-amp, then it has an infinite rejection ratio. In the same case, if we use the same kind of op-amp here in the second case, even when the op-amp is having an ideal gain and all those things in both the cases, in the second case, you are having a PMOS transistor with a finite impedance, right? So at a very high frequency, you can say this particular R out of the PMOS transistor will dominate your power supply rejection ratio. So that is what is normally the problem in case of you are using a PMOS transistor for the load. Another, directly you can say that, so this is just a build-up process for next one. So in place of PMOS transistor, I can use an NMOS transistor, right? Huh? Why? No, I didn't get it. Okay. Yeah, so why PMOS fails to suppress at a higher frequency is, so you can say at a high frequency, the gain of this loop gain will actually is going to fall to zero. You do not have any control coming in, right? At that time, you will have a PMOS transistor where gate control is close to zero, right? You have, it's like not controlled at all. Something here. Whatever cap is here, you will, that is fine. I'm not, my loop is not working anymore. Then this equivalent is what you have. You have for this, if this gate control, you are assuming that this is going to be zero, then whatever, let's say you have RDS, one resistance, means if I assume that VDD and these two are shorted, gate is shorted, so VGS is going to be zero, you have only RDS of this transistor, and you have whatever R on of the R equivalent of the VCO. So this is what you will have, right? And the loop doesn't work. Okay. So that is at a higher frequency, this is going to dominate. Okay. And things will change if in place of PMOS you are using an NMOS. So we will now study what kind of different regulation can work better for your VCO. So the next topic will be, any question before I start the other topic? So this will, next will be your power supply rejection in case of all your ring PLL. So we have completed so far a whole analog, integer and ring PLL, right? I think I haven't missed any block as such there. Okay, so you can very well design a ring PLL now after this. Now the next one is, because we are considering the regulation of the VCO, it would be good if we start with the power supply noise in ring PLL. Okay, ring PLL means it's using a ring oscillator in the PLL. So what automatically changed. So we have phase frequency detector followed by charge pump. Okay, this goes to the loop filter. We are using a passive loop filter so far. And then we are using an op-amp regulated. Which particular transistor are we going to use? That's we will decide later. But let's say you are having some bypass transistor here. This is VCO, and the output of the VCO is coming with the divide by N, and this is your reference. So phi in, and this one is phi out. Okay, F in and F out, you can say, right? So now the thing is, in all these blocks, because they all are, so one thing is, why are we worried about this VCO noise and all, is that this VCO noise can actually add up to the jitter in the system. That is all. And why will this VCO will have a noise? It can, whether this noise coupled from the other blocks or any kind of glitches, because of any digital block doesn't have the power consumption static all the time. So you will have a supply ripples, and these supply ripples should not ideally cause any trouble to the VCO output jitter. So the metric to measure for the, that is measured with the power supply noise, with power supply noise rejection. Let me check it whether it's a rejection or ratio. Noise ratio. So I think it's a ratio thing. I will confirm this thing. This is what for this PSNR, and this is defined as in dB, which is 20 log to the base 10, and delta of T jitter at whatever the normal period at the output divided by delta VDD. Okay, this is the definition of PSNR which you measure uh, when you want to verify, when you want to see what kind of jitter does it introduce at the output with a given supply voltage. Now, something which can be confusing here in this case is when I am considering a delta VDD of 10 millivolt on 1 volt supply, or am I considering a 10 millivolt on 5 volt supply? See, 10 millivolt on 1 volt supply is a lot more noise than considered to a 5 volt supply, but that's the way it is being defined. You specify at what which you measure. Okay, and the other thing you can say that the argument of the logarithmic is not dimensionless, which is ideally it should be dimensionless. So you can consider this is like 1 volt. Means I would say this is the definition which we are using. The confusing part is the dimensionless of the argument and whether this ripple is with respect to 1 volt or 5 volt. But you take that, and when you read any power supply noise number, read that number at which supply it is being measured, because that will specify what kind of percentage ripple you can have it. So now all these digital blocks can have a noise at the out on their supply, and this one is VDD. So op-amp VDD can also have that. Okay, so they all have this noise. What we need to find, or when we compare any kind of PLLs with respect to the power supply noise, we consider this metric. Okay, now in this case, okay, this also has a supply, so the noise is present here also. Okay, now, pardon? Yeah. It is means if you are considering the same percentage for my, I would always see what supply voltage it is, and I would always consider what percentage of the supply ripples am I considering. So what I means, you can say if I have a 10 millivolt ripple on a 1 volt supply and 10 millivolt ripple on a 5 volt supply, I would expect that 5 volt supply might be better than for same millivolt ripple, right? Means consider a simple logic. So okay, let me just bring this. So let's say I am using this inverters as buffer in the VCO, right? Okay, and if this buffer is operating with a 5 volt supply, okay, and I have any, so what happens is, let's say the input is clean for this buffer and the output will be jittery, right? Now this output is jittery if I am using a 5 volt supply and I am considering the same noise of 10 millivolt, right? So the slope for this 5 milli, and if I am considering same rise and fall time, means this is very much considering apple to apple kind of thing. We're considering same rise and fall time from 0 to 10% to 90% of the supply. Then in that particular case, a 10 millivolt in this kind of buffer will cause a lesser jitter as compared to on a 1 volt supply. Right. So if I look PSNR for this, for the same clock at different, same clock frequency output at different supply voltages, I may get a better PSNR for a higher supply. This will be there for certain blocks. You can have that. So it's always important to see what kind of supply are we considering. So when you go to a lower supply, like a lower technology node where your supply voltage is getting limited, right? Same 10 millivolt now will cause you a more jitter in the output, which would not be a problem at a higher supply voltage. Any question? Right? Okay. So in these cases, your PFT divider, they both are the digital blocks. Your charge pump is operating with the pulse width modulated things. So if I look, so let me just say for PFD, what can happen? So the PFD which we have seen as a 3-state phase frequency detector, reset, we have up and down, right? This was VDD, means this was tied to VDD, supply was VDD here, D, and this one was clock, which is reference. Sorry, yeah. And then you have on the other case, you had the feedback clock. So let me just say F out by N clock. And this one was also tied to VDD. And this has a supply. Sorry, supply VDD. So if I'm having any noise on PFT, the noise is here and here, right? Ideally, these up and down pulses. So let's say this is up, and the down pulse in case of a some offset thing, you will have up and down, right? Now, if you are using a CMOS logic, right, with the whole 0 to VDD swing, the disturbance which you will cause here due to the supplies will be lesser in case of CMOS logic. It will surely there, means it is not that it is 0, but it will be lesser in case you are using a CMOS logic, right? Because the gain of the all this logic is pretty high. Ideally, what you want, as soon as the clock changes, my output goes high. So you will be working slightly in that region only. So it might be negligible, but it is there. And what will the supply noise will cause while causing this change in the output time instance? They will cause a delta change here. And this delta change will then translate to your output. Okay, so you will measure the what is the delta change because of the supply noise and up minus down pulse, and then you can calculate what is the output jitter contribution. Similar will be the case for all your buffers, which we have seen how the buffer edge changes and it is getting accumulated. Now the thing is about the charge pump. So if I have, so let me, sorry. This is for considering the supply noise of the charge pump. So these are all switches up and down, and ICP, ICP. So let me call this as I up and I down. Okay, if I can maintain I up and I down as ideal current source, then supply noise will not do anything, right? No, that doesn't come. The current which is being pumped into it, that's the thing, matter. But all these current sources are real current sources which have a finite impedance. And in that finite impedance, if the impedances are not matched on top and bottom side, then you will have some delta change at the output. And that also is a contribution only when both the switches are on. So if I up and I down are mismatched, your impedance path is not the same, then you will have that delta leaking into the loop filter. Okay, so this is PFT and charge pump, and the next one is the case of the VCO, which is the most important one. So let me put it this way, that you have a VCO, and let us say you have this VDD, and this is the actual control node of the VCO, right? So right now I'm not controlling, not showing you the whole loop in order to find how the VDD noise is contributing to the output jitter. You find the transfer function from VDD. This is all any incremental change. You need to find this part. Okay. And if you assume, let's say this is equals to K some VDD, the control, the transfer, the gain from a supply to the control voltage of the VCO, then your omega out, which was earlier only KVCO times V control. So your omega was KVCO times V control. Now the V control has an added one due to the gain from the supply noise also. So you have KVCO times V control 0 plus KVCO times KVDD times VDD of whatever the gain, a small signal which is coming from the supply, right? And your delta of phi, which is basically the additional phi which is coming due to the supply noise, is KVCO times KVDD times VDD noise. So let me just call this as VDD noise. So let's check this part. Okay, so VD noise times GD. This is delta phi out. And the way we calculate the supply noise sensitivity of the VCO or in the whole loop is we apply a small signal on the supply. This is while you are measuring any supply noise thing. Means you can do one kind of analysis in PSS and PSC. That's a different case on a PLL in simulation. But the way you measure in case of a real PLL chip is you will apply a small amplitude, sinusoidal amplitude on a supply, and then you measure the jitter at the output or phase noise at the output. So that is, so when you're applying, so let me just say you apply some amplitude A, AVDD times at a given frequency cosine of omega nt TD. Okay, sine or cosine, whichever way you want to consider, we can consider that. Okay, so this one is KVCO times KVDD times AVDD. Okay, now this is divided by omega n into cosine of omega n. Okay. So what will be the PSNR when we are considering for the supply noise only from the VCO is 10 times log to the base 10. This is delta phi, and we saw delta t by t, right? So I will have a 2 pi factor here, and that should be divided by the amplitude of the noise. And amplitude of the noise here is AVDD. So we are considering here, let's say, the maximum amplitude change you can get. So this will be KVCO times KVDD by omega n and 2 pi. Okay. So the important thing which you can see from here is that if I have a larger KVCO or KVDD, I have a large PSNR, power supply noise. Means I have a large noise due to the supply, means large jitter due to the supply noise in the VCO. Okay, and the other thing which you can see from here is that this is having a low pass filter response with respect to the omega n. Higher the frequency, lesser is the noise contribution at the output. So this is what your VCO is doing. We are looking at a phase noise or the integration part. So this is where you see the integration part of the VCO coming in. Okay. Any questions so far? So okay, since the time is not there, we'll stop here and we will go through this whole PSNR of the op-amp in much more detail, what kind of op-amp you can use, suppression and mitigation, both the techniques. Okay, so let's stop here.